So we're in section 1.6, or is our projector not on? Yes?
Why does that clock second hand not work?
I don't know. It's funny because I bought one of those clocks because this clock over here, oh look, it's working. That's the first time I was a sub here before I became a teacher. So that was like, I don't know, 6 years ago. And that clock has never worked.
Really?
And now that's the first time I've ever seen it work. Anyway, I bought one of these clocks, and when that clock didn't work, the second hand stopped right there.
Yeah.
I took it back, I exchanged it, brought this one back. Second hand stopped in exactly the same place. I was like, I'm not even gonna.
But it still works though, yeah.
Yeah, and it sets itself by the atomic clock. So every once in a while, it'll go and set the time to the atomic clock. It receives a signal from the atomic clock.
What about the clock to your left and
This one doesn't work. That one does. I contributed to a Kickstarter, and they're shipping my clocks that the Kickstarter people manufactured. I'm getting some new clocks. They're really cool. All right, inverse functions. So when we say inverse function, what are we talking about? What do we mean? What does inverse mean? What was it? Someone said something. Opposite. Okay. So that's not a bad. It's not a bad word. What do we mean by opposite? One thing we do in math is we try to make our words, our definitions precise. So what do we mean by opposite? Let's think about opposite
negative reciprocal
operation. So something like negative reciprocal. So that's kind of opposite. Let's think even easier than that. Thinking about arithmetic. What's the opposite of addition? Subtraction. Opposite of multiplication? Division. So what does addition do to subtraction? Cancels, or I thought someone said undoes it. So inverse functions undo each other. Now let's zoom in on this a little more. What do we mean by undo? What kind of, can we think of a pair of functions that undo each other? Think about solving an equation. What do we do? Let's say if we had like x squared equals 5 and we wanted to solve for x. What do we do? Square root. So what does the square root do to the square? Undoes it. So square root and square are inverses. So what did we do to the one function to undo it? When we square the square root, what are we doing to that function? What did we just do in our lesson from Tuesday? How did we put those two functions together? We made a composite function. We made a composition. So that's what we mean by undo with inverse functions. Compositions undo each other. So that's how we're going to define inverse functions. We're going to say that f of x and g of x are inverses of each other if and only if, and when we say if and only if, we mean it works both directions. If f is, we can say if A then B and if B then A. So both the conditions are true. It works either way we say it. If and only if f of g of x equals g of f of x, and they have to undo whatever they do to x. So when we make the composition, all we're left with is x. We take x, we plug it into g, then we plug it into f, plug that into f, we end up with x. Same thing if we form the composition in the other direction. So when we form the composition in either way, we end up with x as a result. And we have to be careful that the domains of each function work with each other. We're not going to write all that down, but this is our test for inverse functions. So if the problem asks you to verify and there'll be homework problems like this, verify that f of x and g of x are inverses. And it might say verify algebraically or something like that. What it's asking us to do is form our composition, f of g of x and g of f of x. And both of these have to equal x. That's how we verify that those functions are inverses of each other. Both the compositions give us x. So some of the homework problems will ask you to do that. We did some of those problems like that in the last set of homework. We formed f of g and we formed g of f, and the problem asked, are they equal? Well, here they have to be equal, and they have to equal x to be inverses. And the way we write inverse, we write f minus 1 of x. So we say this is the inverse of f, or f inverse. And be very careful with this. Most of us won't make this mistake, but sometimes students say, we want to make sure we don't say that f inverse, that does not equal 1 over f. When it's not the reciprocal, it's the inverse. The reciprocal is the inverse of multiplication, so that's why we get those two confused. So when we have inverse functions, some certain special things happen. And there are other ways, if we look at a function in a different way, we can tell if we have inverses or whether or not we have inverses. So, table of values. Do we remember what inverse functions do to the x's and the y's in a table of values of functions? They switch them. Perfect. Table of values. They switch the x's and y's. The domain turns into the range turns into the domain. So if we have a table of values like this, and we form the inverse, it's going to switch the x and the y. Switches them around. Graphs. If we're looking at the graphs of two functions, how do we tell if those, by looking at the graphs, if we have two functions graphed, how do we tell if those two are inverses of each other? The graphs of inverse functions do something special. You remember what they do. It involves a reflection. Do you remember? It reflects. Wait, what did you say? Not the x or y axis, so it involves a reflection or involves a line. Not over the y axis.
The y equals x.
There we go. The line y equals x. Is that what you were going to say? They reflect over the line y equals x. So if we have two graphs, and it says, are these two, do these graphs represent the graphs of inverse functions? Y equals x is the diagonal line that goes right between the x and the y axis, slope of 1. If this is our function, we reflect over the line y equals x, and our inverse function would look like this. So this is just one example. So we have to reflect over that diagonal line y equals x for those graphs to represent graphs of inverse functions. If they reflect in any other way, they are not inverse functions. So if we're looking at two graphs of two functions, that's how we tell by looking at the graphs. All right, good so far. All right, a couple more things about the graphs. So we're still talking about graphs. Functions. If we look at a graph we're looking at some graph. How do we tell if that graph represents a function? There's a test. Vertical line test. Functions. Graphs of functions, pass, vertical line test. If we have a graph of a function, then how do we tell if it has an inverse? There's another test. What did you say? Horizontal line test. It has an inverse. If it passes the horizontal line test. So just a couple quick drawings here. So this would represent a function because it passes the vertical line test. I draw and what that means is a vertical line only touches it in one place at any time. So there's my horizontal line. So we're going to say this one passes the horizontal line test, so it has an inverse. If I graph a function like this, a horizontal line hits this graph in two places. So this one fails a horizontal line test, and it has no inverse.
So if you did it like with that one, if you flipped it over the x-axis, that would be the inverse of it?
This one?
Yeah.
It would, well because this function does not have an inverse. So if we flipped it over you said the x-axis?
Yeah.
If we flip it down this way?
Yeah.
No, that would not be the inverse.
Right.
Because this doesn't pass a horizontal line test, so it doesn't have an inverse.
Right.
What can we do to this function to make it have an inverse? Could we restrict it somehow? Great, okay, that would work. If x is greater than 1, we take that part off. Now it passes the horizontal line test. So if we just restricted the domain, we could get an inverse. We'll do that with some functions later in the year, where we restrict their domain so they have an inverse. So this is how we tell, if we look at a graph, whether or not a function has an inverse, if it passes the horizontal line test. So is this all bringing back some vague memories about inverses?
Yes.
Okay, good. We call a function with an inverse 1-to-1. So if a question asks you, verify that this function is 1-to-1. If it has an inverse, then it's 1-to-1. That's how you tell if it's 1-to-1. Does it have an inverse? If the function is 1-to-1, that means we have no repeats in x or y. So if we have a table of values or we're looking at a graph, no x's repeat and no y's repeat. So the other way we say this is there's one y, exactly one y for each x and exactly one x for each y. So the x's don't repeat and the y's don't repeat. So if I go back here really quickly, here I have repeat y's. Here, let's say y equals 2, and y equals 2 right there as well. So I have a repeat in the y. If I block it off here, I don't have any repeats in the y's. So we don't get any repeats in the x or the y. All right, questions so far? So kind of a reminder about inverse functions. So let me go back really quickly. You'll have problems that say verify that these two functions are inverses. To verify that functions are inverses, you form the composition both ways, and you have to get x out for both compositions. If you're looking at graphs, they have to reflect over the line y equals x to be inverses. We switch the x's and y's. If our function passes a horizontal line test, it has an inverse, and that means it's 1-to-1. Functions with an inverse are 1-to-1. All right, the last thing that we need to do, we need a reminder about, is how we find inverse functions. Do we remember how to find inverse functions if we're given some function? It involves switching something. And we've done you've done this for quite a while now. We switch something in the equation. What does an inverse function do to the x's and y's? Switches them. Find an inverse function. Switch x and y. And then what do we want to do? Remember what we do from there? Solve for y. And then we write f inverse of x. So I want to do a couple of examples of this to remind you about doing this. So to find an inverse function, if you're given some function and it says find the inverse, switch the x and y, solve for y, write f inverse of x instead of y. So let's look at an example. Let's say that f of x equals x cubed, not x cubed, cube root of x minus 5. And we want to find the inverse. Well, I don't have a y here. What do I do? What does f of x mean? Isn't that the same as y? I'm going to write y equals the cube root of x minus 5. F of x is the same as y. Now I'm going to switch them. Everywhere I see an x, I put y. Everywhere I see a y, I put x. X equals the cube root of y minus 5. How do I solve for y now? Cube both sides. X cubed equals y minus 5. And now I'm done. Y equals x cubed plus 5. And now I write f inverse. F inverse of x equals x cubed plus 5. And there's my inverse function. And if it asks you to verify that this is the inverse of this, we would form the composition both directions and show that we end up with x. Questions there? Yes?
What do you mean by form the composition?
So if I wanted to form the composition, I would do the cube root of, I'm going to plug this in for x. X cubed plus 5 minus 5. So I'm just plugging f inverse in for x. And this gives me the cube root of x cubed, which is x. And then if I wanted to go the other direction, I would do the cube root of x minus 5 cubed plus 5. And this would just be the x minus 5 plus 5 equals x. So just make the compositions like we did in last night's homework. Just rather than with f and g, we do it with f and f inverse. Okay? All right, one more, a little trickier this time. Same thing, we want to find the inverse. F of x equals x minus 4 over x plus 2. And I want to give you a hint. F inverse does not equal x plus 4 over x minus 2. And F inverse does not equal x plus 2 over x minus 4. We can't just switch the signs. We can't just flip this fraction. We have to do a little more work. So I'm going to go through this kind of quickly because we're short on time. Y equals x minus 4 over x plus 2. Write f of x as y. Switch the x's and y's. Everywhere I see a y, I write x. Everywhere I see an x, I write a y. X equals y minus 4 over y plus 2. I want to get rid of this fraction, so I multiply both sides of the equation by y plus 2. So these cancel, and I get x times y plus 2 equals y minus 4. Distribute here, because I have these two y's. So I need to do some work to get rid of those two y's. I'm going to distribute here. xy plus 2x equals y minus 4. Now I'm going to get all the y's, all the terms that have y, together on one side of the equation. So I'm going to subtract y and add 4. So I subtract y from both sides, add 4 to both sides. So I get xy minus y, subtract y from both sides, equals, sorry, I don't want to subtract 4, I want to subtract 2x from both sides. Minus 2x minus 4. So I subtracted y from this side and this side, I subtracted 2x from this side and this side. Here's where most people get stuck. What can I do here? I want to get y by itself. I have a y in each term here. Factor out a y. Very nice. I'm going to factor y times x minus 1 equals negative 2x minus 4. Now I'm home free. Solve for y, divide by x minus 1. Y equals minus 2x minus 4 over x minus 1. And I write f inverse. And I'm done. So a little more work than just flipping the fraction or changing the signs. So this problem with fractions is the type of inverse that gives people more trouble than the others. All right, homework. Oops, 1 through 6, 7 through 55. EOO, every other odd. There you go.